Ever wondered how multiple users can interact with a computer system simultaneously? Well, the answer lies in a clever piece of computing wizardry known as time-sharing systems. These systems, also known as multi-programmed systems with time-sharing, are designed to support multiple users or tasks concurrently by rapidly switching between them, a feat that gives the illusion of simultaneous execution. At the heart of time-sharing systems is a principle known as multi-programming. Much like batch processing systems, time-sharing systems use multi-programming to keep the CPU busy, allowing multiple programs to run concurrently. But here's the twist. In time-sharing systems, the CPU's time is divided into tiny slices, often referred to as quanta. Each program is then allocated a small portion of CPU time, a process that allows for rapid switching between tasks. This rapid switching is managed by something called CPU scheduling algorithms. These algorithms, which include round-robin or priority scheduling, aim to provide fair access to CPU resources among competing processes or users. By doing this, time-sharing systems can offer quick response times to user inputs, a feature that prioritizes user interaction. But how do multiple users interact with the system simultaneously? That's where terminal handling comes in. Time-sharing systems support multiple terminals or user interfaces. Each terminal provides a user with a dedicated interface to execute commands, run programs, and access system resources. Underpinning all this is memory management. Time-sharing systems manage memory resources to accommodate multiple concurrent processes or users. Techniques such as virtual memory may be used to efficiently utilize available physical memory and provide each process with a virtual address space. Of course, with so many tasks occurring simultaneously, there's a need for concurrency control. Time-sharing systems implement mechanisms to ensure that concurrent access to shared resources, such as files or devices, is properly managed to prevent conflicts and maintain data consistency. Lastly, we have context switching, the process of saving the state of a currently running process and loading the state of another process for execution. In time-sharing systems, context switches occur frequently to switch between different user tasks or processes. So that's the basic concept of time-sharing. But how does it work in detail? Let's dive in. A key feature of time-sharing systems is multi-programming. This means that the central processing unit, or CPU's time, is divided into small slices, also known as quanta. This division allows multiple programs to run concurrently, creating an illusion of simultaneous execution. Now you might be wondering, how does this work? Well, during each time slice, one program gets a turn to execute its instructions. Once its time slice is up, the next program in line gets its turn. This rapid switching between programs occurs so swiftly that it appears as if all programs are running at the same time. This method is highly efficient as it keeps the CPU constantly busy, rather than idling while waiting for a single program to complete its tasks. This constant activity maximizes system efficiency and allows for quick responses to user inputs. So, in essence, multi-programming ensures that the CPU stays busy, maximizing system efficiency. But how does a time-sharing system decide which program to run next? This is where CPU scheduling comes into play. Imagine a bustling city intersection. The traffic lights, acting as the CPU scheduler, regulate the flow of vehicles to ensure each one gets a turn. Similarly, CPU scheduling algorithms manage the flow of processes, deciding which one gets to use the CPU next. There are various types of scheduling algorithms, such as round-robin and priority scheduling. Round-robin scheduling is like a game of musical chairs. Each process gets a limited time slice or quantum to use the CPU before it's the next process's turn. On the other hand, priority scheduling operates more like an airport check-in queue. Priority is given to processes based on certain criteria, such as urgency or resource requirements. This ensures important tasks are not left waiting in the wings. These algorithms play a crucial role in maintaining a balanced system. They prevent any single process from hogging the CPU, ensuring everyone gets a fair share. CPU scheduling algorithms help to maintain fairness and prevent any single process from monopolizing the CPU. Now let's talk about the user's experience. how do time-sharing systems manage to respond so quickly to user inputs? In the world of time-sharing systems, the emphasis is on user interaction and responsiveness. This is crucial as these systems are designed to serve multiple users simultaneously. So, how is this achieved? The answer lies in the principle of interactive response. Interactive response is the concept of providing swift feedback to user inputs. In a time-sharing system, this is accomplished by rapidly switching between different user tasks or processes. This switch happens so quickly, we're talking milliseconds or microseconds, that it gives the illusion of multiple tasks being executed concurrently. This rapid task switching ensures that each user receives a prompt response, thus providing an interactive, user-friendly experience. But how does a time-sharing system accommodate multiple users at the same time? This is where terminal handling comes into play. In the context of time-sharing systems, terminals refer to the user interfaces or access points through which users interact with the system. Each terminal offers a dedicated interface for a user to execute commands, run programs, and access system resources. This means that multiple users can engage with the system simultaneously, each from their own terminal. However, it's not just about quantity. Quality matters too. Each terminal must provide an efficient, responsive experience. This is achieved by the time-sharing system's ability to rapidly switch between different user tasks. Remember, we're talking milliseconds or microseconds here. By efficiently managing interactive response and terminal handling, time-sharing systems can offer a seamless, interactive experience to multiple users at once. The rapid task switching ensures that each user receives a prompt response to their inputs. Simultaneously, the multiple terminals ensure that every user has a dedicated interface for interacting with the system. This combination of rapid task switching and terminal handling is what makes time-sharing systems so effective at handling multiple users simultaneously. It's a delicate balancing act, but when done right, it allows for efficient resource utilization and high user satisfaction. So through rapid task switching and multiple terminals, time-sharing systems can effectively handle multiple users at once. But there's more to time-sharing than just CPU management. Memory management and concurrency control are also vital. Let's delve into memory management first. In time-sharing systems, multiple processes or users are concurrently active. This means they all need a piece of the memory pie. To accommodate this, time-sharing systems employ techniques like virtual memory. Now, what's virtual memory? It's a method where the system uses part of the hard disk as an extension of the RAM. This means that even if the physical memory is fully occupied, the system can still keep running smoothly by allocating virtual memory space on the hard disk. The beauty of virtual memory is that it gives each process its own virtual address space, creating the illusion that it has the entire memory to itself. Now, let's move on to concurrency control. Concurrency control is the practice of managing simultaneous operations on shared resources like files or devices. Let's imagine two users trying to update the same file at the same time. Without proper concurrency control, we could end up with data inconsistency or conflicts. To prevent this, time-sharing systems use various mechanisms like lock-based protocols or timestamp-based protocols. These protocols help to maintain the order of operations and ensure that only one process can access and modify a shared resource at a time. But what happens when a process is waiting for a locked resource? The system doesn't just make it twiddle its thumbs. Instead, it uses the waiting time efficiently by letting the process perform other tasks or by switching to another process. This concurrent execution of processes is a significant aspect of time-sharing systems that helps to optimize CPU utilization and response time. So, memory management and concurrency control are not just about running multiple processes at the same time. They're about doing it efficiently and consistently. They ensure that all processes get their fair share of resources, that data remains consistent, and the system keeps humming along smoothly, no matter how many users or tasks are vying for its attention. By controlling memory and concurrent access, Time-sharing systems ensure efficient resource utilization and data consistency. Finally, let's discuss context switching and security measures in time-sharing systems. Context switching is like a master juggler in action. It's the process where the operating system saves the state of a currently running process and then loads the state of another process for execution. This switch happens so frequently and seamlessly that it creates the illusion of multiple processes running simultaneously. Now, imagine if this juggler starts dropping balls, chaos ensues, right? That's where security comes into play. Time-sharing systems enforce strict security measures and access controls to safeguard system resources and prevent any unauthorized access or interference. These measures are crucial in ensuring that all processes remain in their own protected space, preventing any potential conflicts and maintaining data consistency. In essence, it's like having a vigilant security guard, ensuring each process stays in its lane and plays nice. Through context switching and robust security measures, time-sharing systems can maintain high responsiveness and protect system resources. So, that's the breakdown of how time-sharing systems allow multiple users to interact with a computer system simultaneously. It's a symphony of components and processes, all working in unison to create an environment where users can operate concurrently, while the system maintains the illusion of simultaneous execution. We've discussed the role of multi-programming, where the CPU's time is divided into small slices, each allocated to a different program, giving the sense of concurrent execution. We've covered CPU scheduling, which determines the next program to run, ensuring fair access to resources. We've explored interactive response and terminal handling, which prioritize swift responses to user inputs and support multiple user interfaces. We've delved into memory management and concurrency control, which manage system resources and prevent conflicts during concurrent access. We've also touched on context switching, a process that ensures smooth transition between tasks, and the security measures put in place to protect system resources and prevent unauthorized access. Understanding these components and how they work together can give you a deeper appreciation of the complexity and elegance of time-sharing systems.